Yep. So there'll be a note sheet out either there or over on the table every day, unless we don't finish the note sheets from the day before. Yes. So a postulate or axiom is a rule that is accepted without proof. We don't need an example of it. We don't need to show that it holds true. We will just accept it as a fact. A theorem is a rule that can be proven. Is a rule that can be proven. So throughout the course of this year, every single theory or theorem, a lot of them, there might be a few I don't go into detail with because it's very tedious in showing, but most of them we will go through and prove them. Okay? And with a lot of the theorems and whatnot, we're not going to be able to assume anything is true until we've proven it, or proven that the theorem is true. Once we do that, then we can assume it is true. Okay? So just because something looks like it is doesn't always necessarily mean it is. And those are our two big things with theorems and postulates. They also have something called lemmas that come from it. So it's almost going along the lines of this theorem is nice, it's cool, and from it, what we can get from that theorem follows these kind of proofs or theorems from them. And if a theorem comes from a theorem, we actually don't call it a theorem. We call it a lemma because it's coming from the theorem itself. Now, the first one we have is something called the ruler postulate. Don't write all that because this is a lot of the technical jargon for it. But the ruler postulate, I'll go on and read it. The points on a line can be matched 1-to-1 with real numbers. The real numbers that correspond to a point is called the coordinate of the point. The distance between A and B, written as AB, is the absolute value of the difference of the coordinates AB. If you take the two coordinate points and subtract their given values, you'll know the distance between them. That's it. And they say the absolute because, again, distance is always positive. It's always a positive value. So, and we're going to kind of use this for measuring using the ruler postulate. So if I want to measure this line to the nearest centimeter, so we'll need to take our ruler and measure it with centimeters. And go and measure and see what you get. Yep, so that's the centimeters. So my ruler is just not to scale as what the paper is, so it's reading differently. But what did y'all get when you measured this line? Y'all agree with 5.2? And that's how we would do this. Now, according to the ruler postulate, well, T is sitting at location 5.2. What was point S located at? 0. Now, this is how we normally measure, because if I'm going to measure something, I zero one out and have the other location. So according to the ruler postulate, this distance would be the absolute value of 5.2 minus 0. Well, 5.2 minus 0 is just 5.2, and the absolute value of 5.2 is 5.2. So the reason that this is helpful is because if we didn't actually have a 0 marker, any other location, I could start at 2. This distance is still going to be the same. We just have to subtract that 2 from it. to actually figure out the distance from one end to the other. But if we actually have a ruler, I don't see the point why we don't just have one be 0 and just measure it to where it sits. Easier. I don't have to do it that way. But that's it. All right. So we kind of understand how a ruler works. Okay. I'm going to worry about, because I put those in the past and you don't actually do anything with it. I hope at this point everybody knows how to use a ruler. Although in years past I've had to teach how to use a ruler, so it's neither here nor there. The other part this here we won't have you doing this here because I'd have to trust some of you with a sharp object. What we can do is we can use something here called a compass. Now, most of y'all know what a compass is because you've used it to make circles. Because it opens up, it looks like a V. Looks like this here, and we can open and close it, and then draw circles. But most of the time when I pull it out, that's what it's known for. But one thing that it's really helpful with, especially in geometry, is actually copying shapes and figures and lines. Because if I wanted to, and use this here to construct a line, and I didn't have a ruler, because I want to copy it exactly, that exact same distance, what we can do is actually use this compass. And let's see here if I can. There we go. Because I can open it up to the width of the line. So now this width is the exact same width of that line. And what we can do is we can take it, move it right here, so this distance created here will be the exact same measure as this one here. Kind of makes sense how that works? Y'all, I mean, if you've seen pirate movies or movies in ships where they'll take this here and you'll see them walk it across a map, they're measuring distance. Because you've seen a scale, they'll put a scale on a map for so many miles. And what they've done is they've done exactly what we did here, figured out a certain mileage, and then you can walk it across doing what we did here, copy, okay, that's one length, flip it over, that's a second, that's a third, that's a fourth, and you can actually figure out a distance on a map using this without actually having a ruler to try to figure it out. And the nice thing with this is we can actually make it bigger, smaller. We can do whatever we want with it. Any questions on this so far? Unfortunately, those are very fickle devices, and most of them have actually quite the sharp end. Okay, now before you start copying this whole thing down, I'll actually tell you what to write, because this is the mathematical definition. Line segments that have the same length are called congruent segments. You can say the length AB is equal to CD, or you can say AB is congruent to CD. The symbol, this right here, is congruent. Well, two line segments are congruent if they have the same length. If they have the same length, then they're congruent. That's really it. So what we can say is congruent segments. Two segments are congruent if what? They have the same length. Now I want to draw attention to, and I'll circle it here on the board, or square it, these right here. Because again, when we talked about this yesterday and the day before, we said when we talk about a segment or we're naming a line segment, we have to put the line segment above it. Yes? But if you look at this here, A, B, and C, D do not have the line segments above them. And the reason for this is that we're not talking about the segment A, B. We're talking about the distance from A to B. We're actually talking about AB's length, its measurement. The measure from A to B, the distance from A to B, is equal to the distance from C to D. So we're actually talking about a number. But when we put those line segments back above them, talking about line segment AB and line segment CD, we're actually talking about the lines themselves. The lines are congruent. The shape is congruent. When we talk about congruent, we're talking about the figure itself. When we drop those segments, we're talking about the measure. And that's really unique to lines, or these segments, because when we talk about angles, we'll actually have the measure of angle this. We'll actually have an M to signify measure. Okay, this is the first thing that's actually a part of the homework, is this right here. Determining if the two line segments are congruent. Now, for most of what we do today, we won't need to actually use the distance formula to figure it out. We can actually graph them. So we have JK and LM. Well, we're going to plot these 4 points in a coordinate plane, and then determine whether JK and LM are congruent. Because for those two to be congruent, they have to have the same length, the same distance, yes. So we can start off by plotting point J. Well, that's at -3, 4. X is always first, Y is always second in a coordinate point. X, Y. X-axis goes left to right, Y-axis goes up and down. Any questions on how we plotted point J? We can plot point K. Point K is 2, 4. So that is our first line, J, K, in all seriousness. Are we good with plotting points J and K and making the line? Point L is at 1, 3. And point M is at 1, -2. Are we able to get all 4 points plotted? Awesome. Now, if I want to know the length, now this works well with grid paper because each one of those squares is 1 unit. It doesn't really matter the measure as long as all the units are the same. And hey, they're on straight lines, yes? Well, this is 1, 2, 3, 4, 5. So the length of JK is 5 units. So let's look at the length of LM. We can do the same thing since it's straight up and down. 2, 3, 4. Well, hey, they're both 5 units. So that means that JK is equal to LM, yes? Because they have the same measures. And since they have the same measures exactly, we can say that they are congruent. Yes. JK is congruent to LM. That's it. Any questions on this here? We good with this here? Let's do another one. So plot points A, B, C, and D in a coordinate plane. Then determine whether A, B, and C, D are congruent. So we just need to go on and plot each point. So point A is at -2, 4. So we go -2 on the X and up to 4 on the Y. And that is point A. Point B is at 3, 4. And that there would give us line segment AB. Then we can go to C and D. C is at 0, 2. So we stay right on the y-axis because the x value is 0. And D is 0, -2. Well, hey, we have straight lines again. And they did all these intentionally on straight lines. 1, 2, 3, 4, 5. This one here is 1, 2, 3, 4. So are they congruent? No. AB, CD. What would I need to do to make this say not? Put a line through it. Just like with not equals, how it's an equal sign with a line through it, we can say not congruent by doing the same thing. Or we can put not congruent. AB is not congruent to CD. We feel good with this here? I will provide graph paper for you so that you can plot those and set those up so it's a little bit easier. Okay. I'm going to go on and just erase this. You don't write all this. I put all this up here so that you can see it and whatnot, but a lot of it is should be understandable. It's kind of straightforward. A lot of stuff in geometry is done to a degree that's not necessary, very meticulous in everything that they do. When 3 points are collinear on the same line, you can say that 1 point is between the other 2. Well, yes. If 3 points are on the line, one of them has to be in the middle of the other 2. No matter how you do it, one's got to be in the middle. If they're not collinear, they can technically still be between them, but it doesn't really work. It's not necessarily between them if they are not collinear. Okay, I'm about to blow some minds here. If B is between A and C, then AB plus BC equals AC. Mind blown yet? So if 3 points are on the line, this part, let me draw it, this part here plus this part here gives us the whole length. Mind blown? Really all it's saying, if this is 7 and this is 4, the whole length is, that's it. That is the segment addition postulate. But if I add 2 segments of the line together, I get the whole. If I know the whole line in one of the segments, I can find the other. That's it. That's all the segment addition postulate is. two segments, I can add them together to get the whole. You ready for the next slide? Okay. Find df. Find the measure of df. Well, according to what we've said, de, its length, plus ef will give us df, exactly. Because if I add the two segments together, I get the whole. So what we're saying is 23 plus 35 would be df. So df is, yep, 58. And as you will notice going through this here, I'm going to write all the steps out. So like this one here on the test, if you're looking at it and say, oh, 23, 35, 58, and put df is equal to 58, and don't do the steps, fine, you get full credit, you got it right. If you don't feel as comfortable with it, write it out. Go on and write it out. Because if you get it wrong, I will deduct pretty much most all the points off. Because if I don't see what you did, it's hard for me to get partial credit. I mean, this here, you hopefully should be able to get it right every time. Let's look at the next one. Here, well, again, we said that the length of FG plus the length of GH is equal to FH. Part plus part equals the whole. Well, I know FG is 21 plus. Do we know what GH is? Well, we could find it, but at this point we don't. Yeah. Choose X. Is equal to 36. Well, exactly, you're right, because then I would subtract it from both sides. Telling me X is equal to 15, or the length of GH is 15. So if we're going by the pure mathematical steps, this is what we would do. But obviously we can see that, well, whole thing's 36, this part's 21, 36 minus 21 gives me GH is 15. That's all you have to do. Use the segment addition postulate to find out XZ. Well, XZ is what? The whole thing. So it would be equal to well, 23 plus 50, yes? I'd skip the whole writing out the segments because I think at this point y'all don't need it. So XZ is equal to 73. That's it. I think there might be something written here. Okay? This is not on your sheet. You don't have to write it down. I intentionally covered it up for a reason. In the diagram, WY is 30. Can you use the segment addition postulate to find the distance between points W and Z? Could we use the segment addition postulate to find this length? Oh. If B is between A and C, then we can use it. Between means that they have to be On the same line, they have to be collinear. So when we look at this here, they're not on the same line. We can't. Now, it might be tempting to say Pythagorean theorem because that is a triangle, 3 sides, a squared plus b squared equals c squared, but that only works if this is a right angle. So the Pythagorean theorem only works if it is a right triangle. It looks like it could be, but because we don't know if that is a right angle to make a right triangle, we can't use it. How would y'all go about finding KL? Any questions on any of this here? We feel good with this here? We don't need to see another one of these? No? So we have 2 more of these here. I'm not going to worry about them. They're the same thing. They're just real world problems. Essentially, they're doing this here. But that's it. That is all we're doing today.